Okay, welcome back to the 424 School of Engineering, everyone. This is module number 4. Today we will talk about CAD design of the 424 car. We'll be together for up to 2 hours. And before I start on the CAD design, I want to show you a little bit more about Perrin.com today and the platform, to give you a little bit more insight into how the team is working. Okay. So when you go on Perrin.com is the place where the core team is working. It's also a dashboard where you can see a lot of information, current information of the next meetings, for example. So obviously you're seeing here the current meeting, which is the 424 school. We've got our core team meeting on a weekly basis on the Wednesday, not every week, but nearly. And in the same way you've joined the 424 school, you can join these core team meetings if you want to listen to basically the small group of people who are developing 424, developing the team as well. We also have here the current funding round that we're on. We're raising some money to build a simulator that will be installed at the University of Oxford Brookes, and anyone can contribute to this. And basically the rest is all the messaging that we are using every day to communicate between the contributors. Once a day we get these new statistics coming through automatically. And you can see the number of people who have registered on Perrin.com, the number of contributors. So a contributor is somebody who has got some earned some credits or bought some credit through the funding rounds. And I'll show you in a minute the list of, you can access the list of all the people and see how much everyone has got. And some more statistics. You can also see basically the total amount. This is displayed in British pound here, but you can display it in dollars or in euros. This is the amount of energy or the amount of time and money that we've invested so far on the platform to create 424, develop the project, and develop the platform over the years. This is the total investment to date, and you could compare that as effectively the valuation for the team, the current valuation for the team. Okay. We also have an interest rate paid every day to contributors. You can see at the top, there's a 10% growth per year on the network. So the team is a network, okay? And we have a conservative 10% growth of the network. And everybody who holds some credits or tokens in Perrin see their amount growing by 10% a year. But on a daily basis, you get incremental amounts. And I will explain a little bit more about this in a minute. But it's like an investment, okay? We want everyone who has been contributing to be on the same growth curve and rewarded in the same way. And the fund is the current fund that we are raising for at the moment. And then you can access any of our conversations that we are having with the contributors. Let's have a little example here. The Unity test drive is where we discuss the next test that we have to do with our two test drivers, Damien and Augusto. And you can see here some discussions around when Damien is going to be available next for the test that I want to do. I'm also doing some setup changes that appear on GitHub, and everything is documented on these chats. Okay, so you can come back in history and read what's going on or follow on a daily basis. Another example is the Unity VPP development. This is where Eddie is posting all of the developments he's doing on the dynamic simulation, the VPP in Unity. Each time somebody writes a message with this superior sign, it means that it's been investing 1 hour into the project. 3 signs is 3 hours, and you can see automatically there is a credit added to this account. This is how we convert time into credit into on the pairing platform. You can also filter messages using this tool here. So let's have a look at, for example, so it's based on the subject of the chat. So if I go pairing.com, for example, and I click here, and you see some chats starting with pairing.com. And this one, the pairing.com new features, is where I also developed the pairing.com platform right now. But this is where I will explain all the new features that as we develop them. And when we get more developers, again, everyone contributing as a developer will post the new features and how much time they've spent. And with an image, for example, in this case, there was a new feature added here, and I explained what that feature was. Okay, so you can see as the software develops or the car develops, you can access all the information there. Got some testing chats as well. And then if I come back to, I clear the filter, so I come back to the page where all the latest discussions happen. You can see that we're having discussions every day. Today we're active in 3 or 4 different threads, and then 2 days ago, 3 days ago, 4 days ago. So there's activity every day. You don't even need an account to see this. This is a public open forum, and if I log out, you will still be able to see that. So just go on pairing.com and you will know exactly what's going on live. As we develop, this is going to be the place where the project is basically documented live. And I anticipate that we're going to have a video feed as well, live, where you can, the day we're going to start building the car, you just come on pairing.com and you will be able to see some videos. And then I show you other features. So at the top here in the middle, you have the directory, and that lists the 82 members or contributors by order of amount that they have in the network. So I'm number 1 on this list, and you see how much I own and the percentage of the total projects. And then you've got more people added to this list. Everyone here has either invested money or time into 424, and I'm extremely grateful for all these people that have come to me over the years and added their name on this long list. And it's only the beginning, and I'm sure this list will grow to a much larger level in the future. Okay, you see details about everyone here. You can click on anyone, and then you got access to their personal page and the chats they've been involved in as well. Okay, if I come back to the directory, at the end of this list, you get the panel with the pictures of all the contributors. And again, you can add your name to this today if you invest in the crowdfunding. So this is the way the team is going to work. Now, in the back end of this, at the moment, everything is stored into a centralized database on the Google Cloud system. But as the team grows, and I want this team to become a very trusted place for many, many people to come and invest into the projects we're developing, we're going to have to improve our infrastructure and the user interface. So this software is going to really develop over the years, over the coming years. And I do anticipate that because we're storing value and we're storing account balances and we're storing investments, we're going to actually move the database onto a blockchain decentralized, like where cryptocurrencies are stored. So keep in mind that this is still early days, but the concept of the team is very much in place, and we're just going to keep improving the infrastructure. Another feature actually I'm going to show you now is we've got this public link here. So everybody in the team can add a public link, and you can see I've got mine here. But we also have another public link here that I invite you to click on, and what this one directs you to a Google Drive that you can basically, this is where we store information data. This is like the folders for the team. Okay, so many contributors have added information here. You see this folder called the members exchange area. If I click in this, in fact, you will see there's a lot of contributors in there to different folders. This is where we store certain data analysis coming from Unity. I just give you examples here. We do data analysis for, we have, for example, a lift and cost analysis for around the Nürburgring. If you open here, you're going to have basically the data that Damien has created when he was driving that day, and that is saved the data in this folder, and that can be reused to replay his lap. But there are other folders, like, for example, the ones that I've created here, active power balance. Sorry, not this one. I want to show you, okay, a comparison here. So 600 kilowatts versus 800 kilowatts. And then you've got some files that are called 424 delta time. And if I open one of them, this is where I do some comparisons between two laps, for example. So let it load. Okay. And here you can see these are two laps that have been driven by our test drivers. One is 600 kilowatts with less drag on the car, and the other one is the traditional 600 kilowatts. So this test is specifically an aerodynamic low drag, low downforce test versus baseline. You can see the different speeds. So obviously yellow is the low drag, so it's a faster speed in the straight line, and then the time delta. And you can see where on this particular test, the test one, which is the yellow one, is coming at half a second faster after the full lap. But you can see how the time has been lost and gained in different places. So I just wanted to show you how we store some information in folders. There are some folders, if I come back, there are folders that I only write into, and these are the Perrin424 F1 Perrin.com. If you go on the Perrin424 one, you will find even some images, for example, some old images of things that have been done in the past. Let's have a look in 2017 424 rendering, and here you can see some old images that some of you may have seen on the internet before, some renderings that we did a while ago. It's quite funny to come back in time and seeing some of these images that were created. This was still the LMP1 model in 2017. So the team will always work this way. Access to information should be the easiest possible for anyone, not only the contributors and people who have invested, but actually the members of the public, you listening today. But obviously, creating the data is what takes time and effort, and that's where we can only select a small, group of contributors and experts who can design the car with us. And as the core group grows, the number of followers will grow, and this team will just keep evolving this way. And to finish again, we are on a growth curve of 10% per year at the moment, and this is arbitrary, but it sort of follows the growth of the network. I anticipate that when 424 becomes physical and the growth will accelerate, we're going to increase this growth maybe to a number around 25% a year, which will give more incentive for new investors to come in, and will allow us to raise more investments and follow on this the journey to build what I want to become a better team, the best team in the world we can build together. Okay. So that was it for the introduction today, but I know you're all here for the CAD module. Anybody's got any question on what I've presented so far on the pairing.com platform before we start? If anybody's got any question, want to raise your hand, please do now. Otherwise, I'll get started on the CAD design module now. Okay. Okay. So CAD design, something extremely important and at the core of what we do when we develop such a complex project as 424. We've talked a lot about simulation and modeling, and today it's very much about looking at another piece, again, a core piece of the project, which is that database of 3D information that describe the car and used for so many things downstream, and I'll talk about that. I told you last week I'm passionate about aerodynamics. I'm also really passionate about CAD design. They go hand in hand for me. It's all about creating quality and efficiency in your development process. And I touched on the fact that we are linking Onshape CAD with Bramble Aerodynamics last week. And as I said, everything starts from CAD design, the concept of the car, the information we need to then feed into the dynamic simulation, the aerodynamic simulation. So it's really important to have a really high quality CAD. And I really want to show you today some of the techniques that I use to design 424 and how I believe quality is built at the core of the project this way. So I'm going to talk today about the strategy for 424 of using a cloud native system Onshape, and why it is so important for us to do it with a system that is not effectively a software installed on machines, but actually a software that runs in the cloud from the browser. Extremely important for the team. We'll obviously go into the CADs in Onshape together, and I will go through some examples of how certain parts of the car are designed step by step. And at the end, I'll show you access to some design stories and come back a bit in time of certain parts of the car, the suspension system, how we've designed it. We had Alex in the team creating these design stories documents, and they're really valuable for anybody interested in this case, suspension kinematics. And there is also one piece about aerodynamic design as well. Okay, so the CAD strategy for 424. When I discovered Onshape in 2016, and I realized what it was, I thought, okay, I know that with this tool, the team that I see, the pairing team can exist. We cannot develop a team like the one I want to develop if people have to install certain software with a licensing process that's complicated on their machine, with files being exchanged, so we can all look at the same piece of data, or versioning issues. We need to go back to what we call agile design and what the software industry has created, which is working in the cloud and working in databases where everyone can collaborate in a much more easy way. If you go on the Onshape platform, 424 is quite is featured on the Onshape platform. It's been for a few years, and we're working with them closely. And you will read on their platform, Project 424, the world's first open source electric racing car, is being designed and developed using Onshape simulation. Onshape simulation is the stress analysis tool inside Onshape that we also use to effectively test the stress, do some stress analysis on. A few concepts that really attracted me to Onshape and the decision to shift to Onshape. First of all, it runs on any devices, even on your phone. So they've got an application, you can open the models on your phone, which is pretty incredible, as well as on laptops and any device. The other thing is it's cloud native. So the data is stored on AWS, Amazon Web Services. It's not stored on your computer or your own server. It's a bit like Google Cloud, sorry, Google Docs, if you use that. So it's a database. It's not a file-based system. And you can have more than one person working on the same piece of geometry because you access entries in the database. So it's much more fine way of storing data. So all you do with your browser is you're visualizing the CAD, but the data is coming from the cloud. The other thing with a cloud native system is you can run fairly complex and heavy simulations in the cloud. You don't need a big computer to run these simulations yourself because they're running using compute outside that can be scaled very quickly. So effectively, when I discovered Onshape in 2016, I decided to leave behind the traditional CAD system I was using, and I started this Formula One car. Some of you will have seen it, the Perrin F1 in 2017. And for me, it was a way to see if the tool was good enough to surface the car in the way I want it. And I said before, I don't want to surface too much, and I will show you today the results of that strategy. But some parts of like the front wing of the F1 car, for example, required some surfacing. Since 2017, they've added much more features that would have allowed me to surface this in an easier way. But my conclusion was, yes, that system is good enough to design the car the way I want to design. So as I said, what Onshape allows us to do is global collaboration. You can have anybody from anywhere as long as they have internet access. They can even create free accounts. That's the other part that really attracted me to Onshape is by using public documents, we can work with free accounts and anybody can contribute to the design without having to commit to a paid license. The paid license is basically giving you the ability to design in the private document and closed source design. In our case, we are open source design, so we can have anyone creating a free account and plugging into the project and designing with us if we feel like that person is required on the project. And the other thing they do is what we call agile development, which is having the ability, it comes from the software industry, having the ability to share very quickly a new piece of design, a new idea with, for example, the manufacturing team or some customers or people in operations. So even people who are not necessarily used to CAD, they could say with their phone or their device, they could very quickly navigate through the car and maybe for the assembly of the car, for example, the people in the workshop could use Onshape to see how the car is assembled in a very easy way. So we can do very quick loops of design, testing, modifying, and then iterating again. If I come back on the collaboration features, I said that effectively it's very easy to add more people to the team. The day we're going to scale and the project's going to really become physical and accelerate, Onshape will allow us to scale very quickly and add more people to this design team. But what it has as well is what we call the version management. And the version management is the ability, and you see this versioning tree here, the ability to create new versions and branches and merging. All that terminology is coming from the software industry and GitHub. When you basically have a team of developers that are all creating new features, and when a new feature is being tested and works, you can merge this back into the main branch, and that becomes your master model, if you like. So I hope you understand why I really committed to Onshape for pairing, and I saw a perfect fit between the tool and what I wanted to achieve. And I think it's really going to pay off dividends moving forwards, having this platform as our version of truth and repository for everything CAD. Now, it doesn't mean that everyone will have to use Onshape to design. I anticipate some people in the team and experts are used to other tools. But what we will ask these people to do is, if they want to design in a different tool, we'll ask them to import the CAD into Onshape, and this is where we will store the final versions of the design, whatever needs to be manufactured. And we will have the open source pairing 424 model available for the public, maintained, and it will make it very clear where to find that model once the car exists. Okay, and it will be in Onshape. Any question about this section before we dive into some models together? No? Okay, perfect. So you've seen this slide before if you came to the previous modules. So just at the click of a button, we're going to open this document called the Pairing 424 Architecture. And this is a document where I try and gather all the main information. There are more documents for the pairing project and people who have been contributing to some designs, but I'm trying to summarize all the design into this one document. And this is also where I keep track of the aerodynamic design and development. Okay, so let's open this together. Okay. As I said before, we want to make information accessible in the most easy way possible. So point number one, you don't even need an account in Onshape to visualize. Here you can see I haven't even signed in. Okay, so this is the visualization tool that you have if you open this URL, and you can literally navigate through the car. You can section the car and look through a section this way. This is the aerodynamic model, by the way. So this is what I call the CFD complete assembly. This is the geometry that goes into Bramble CFD. And it's taking geometries from other sections of this document where we basically define the geometry of the entire car. So you can open exploded views if they exist. Some name positions. So if you have a suspension, you could have different position for the suspension and open them this way. And then you can export the CADs. If I go on either select certain parts and export them, or you could export the geometry here. It will come up with, it will ask you in which format you want to export. And as you can see, you can export in all of the main formats that can be read by other software. I typically use Step if I want to have a good quality CAD that is used somewhere else. But when we go to CFD, for example, we use the STL format. The IGS is the older CAD format, and it's lesser quality than Step. But if you Parasolid is the native CAD format that also is used by Onshape, and that can be reused by software like Siemens NX, for example. Okay, you can also create images, and then you can make some measurements. So if I remove that section, and I can just measure, if I want to know the length of the car, I'd go from this point to maybe that point, and the delta X is 4.7 meters. Okay, so this is the length of the car. So you can measure very, very easily. You can even click on a section and you'll see the surface area displayed here. So a very nice tool for visualization. You can also click on, for example, this part and click isolate, and that will show you just the ducts, and the rest of the car is transparent. Okay. From there, imagine you want to see how a certain part has been designed. Let's look at the wheel arch at the front. So let's right click here, and it will tell you that you can navigate to other tabs where this part is coming from. This is an assembly here I'm showing. And typically that specific component has been designed into another tab that's called panels front. So if we go there, okay, I will switch on the navigator here on the left. So on the left here, you see everything is organized in folders. We are now in the body folder, and in the body folder, you find a number of tabs where I have designed some panels specifically for the bodywork. And the windscreen, for example, has been designed there as well. The rear body, the front body, etc., etc. Okay, I'm going to dive into a bit more details of how I design things here. For this, I will need to sign in so I can basically come back through the steps. Here you can see the history tree of design feature for that for these parts. And this is the bar that you can roll back with. But when you are not signed in, you cannot come back in time and look at feature by feature. You cannot even enter into a feature and you cannot see the parameters. So this is the view only, and you're limited into what you can do. So I'm going to sign in now. And if you create a free account, again, you can do that on your side. Okay, so now I am effectively signed in. And we're going to be able to move that bar and look at the different steps for the creation of certain panels on the car. So I explained in the previous aerodynamic module how I like to keep things simple, and if I can design the same component with less features and less parameters, and that the aerodynamic performance is as good, then I will want to go this way. It's the same as when you create code. If you create code and you can write the same, effectively the same function with less lines of code, then it's a better code. Okay, it's easier to maintain, it's easier to understand, to go through, and it's the maintenance that matters. Here we are about developing a high performance car. It's not about just creating one version, looking at it and say, okay, let's go, let's build this. No, we want something that we can iterate on and keep modifying over and over and over. So the value of having something simple that we can iterate and modify quickly is very high in the context of high performance and motorsports. So this is why when you look at components like this, I know through experience that, so this is the front wheel arch. Through experience, I know that we need to create this sort of fillets at the back of the front wheel in order to help, if you like, the flow behind the front wheel navigate on the side of the car and have the better quality. But you could create a complex surface, but this is actually just a fillet. This is just a constant fillet with a flat stop at the top and then a constant blend here. So it's only 3 features or even 2 to create this piece of geometry that is important for the performance of the car. But I'm trying to, you can see how I'm trying to reduce how these important parts are created with the least number of parameters I can. The other thing I do is I try and design in 2 dimensions as much as I can. So if you look from the side view, effectively the top of the wheel arch is an extrude. Okay, so this face, this face, this face, and this face are all coming off the extrusion of a simple side profile. In fact, the profile continues there and there. So you can see the profile is a fairly simple profile from the side. And we're going to go and look at these 2D sketches and how it all starts from. So if I move if I roll back the bar, so what I'm trying to achieve is every tab, you don't want too many features. Here, actually, we don't have so many features. We have 25 features. You can see the list here, 25. I wouldn't want to have more than 100 or 200 features, because to maintain and come back in time will become complicated. But if I roll back to the first feature here, it will show us what we've been designing from in this this tab, which is a part studio. Okay, so actually, this part studio, the aim of this one is to is to take a master. This is what I call a master. You can see it's the general shape of the panels around the front wheels, but they're as one block. And in this case, it doesn't have any thickness in some areas. It has some thicknesses in this area. It's a thin shell, but some other areas are plain. So it's coming from another tab. And the aim of this tab is purely to split the panels and finish them as finished panels. So effectively, if you advance here, we have the creation of a sketch, which is a 2D profile here. And that basically defines where the parts are going to be split. And then we've basically extruded and split the master. This is basically the profile of the side of the chassis. Then if we go a bit further and advance a bit further, a few more steps. Okay, now you can see that we've split with a sketch. So I'm going to show the sketch here. So we have one sketch here. You see that simple square. This is the definition of where we split the panel, because obviously there is an assembly requirement here to remove the arch, but keep some parts on the car. Okay, and now you can see that we've actually have the hollow part now of this, and also the creation of the brake ducts. If I come back a little bit in time, I just check if the brake duct was already part. Sorry, the brake duct was already part of this master. We'll come back to the other tabs where the masters are created. Okay, so we are basically splitting the model, and we are doing the mirror at the end. So we've got the right-hand parts, and these fillets are. This is okay. So what we've been creating here is the dive plane. So you see this 2D sketch, very simple again, just in the YZ plane. We've created this very simple sketch here in 2D. There is a thickness associated. That's been extruded to create the dive plane. And the fillets is basically to finish that corner instead of having it sharp. So if I come back two steps, we were having a sharp edge here and a sharp edge there. And all I did is to create two fillets, and now you see the top profile is finished. So really trying to have the least number of features. So let's see where that master is coming from. So if I right click on it, it will tell me that I can switch to master body front. Okay. So here we have the master for all these panels is coming from this tab. And effectively we've created this complex shape And it's all happened here, and it's got 76 features. Again, I'll always come back to number of features. I want to understand the complexity and how much effort it is to change anything. Remember that if I want to change the volume or the shape of this wheel arch to go in CFD, I have to come back to this tab, and I have to very quickly understand what I need to change so the whole shape will be affected. Let's take a look. You can see at the beginning we always have some sketches. If I double click on this sketch here, this sketch is what defines the side profile of my wheel arch. Typically, you're going to have some important parameters. That's 690 here. If I reduce it, you will basically close the opening behind the front wheel. If I click Final here, it shows me the end result. I am still in the sketch, but it shows me what the wheel arch is going to look like if I change a number. Let's have a look. If I was to change the 690 to, typically I'll reduce it by maybe 25 millimeters. So I'll go to 665. There's going to be some issues there, I can tell, in terms of the fillet is not going to work. But anyway, you can see how the shape has automatically been affected. If I come back one step, okay, you can see the opening changing at the back of the front wheel. That's typically a test I would do in aerodynamics. I would do that sort of 25 mil change. I would expect by closing the exits behind the front wheel. By the way, we'll have to repair. There is a feature missing now. You can see the hole is gone. And if I go into my history tree, some of the features will become red, so they were not able to rebuild. So I'll have to go and manually understand what's happened there. And maybe some features have become too small and the fillet has fallen over, and we'll have to repair that. You can see why it's important to keep it simple so we don't have to repair too many things. But yes, typically if I close this exit, I'll go to aerodynamic test in CFD. I would expect the pressure under the wheel arch to increase a little bit, which will actually reduce the front downforce, but the drag will reduce as well because we have less dirty air coming out. Okay, so typically a test like this would be done. I can see there's an issue here as well with this detail. So if I come back to the original shape, you can see the fillet is clean. We have this cut on the side here, but when I changed my parameter, I have some quality issues to resolve. The reason for that is because you can see this big fillet on the sides has eaten into, it hasn't finished before this point here. If I come back there, you can see now it's higher. We have a clean straight face, and now the fillet can work. So we'll have to change another parameter. We'll have to change the size of this big fillet on the side to make this work. I will not try to do that today. I just wanted to show you how I work. And I'm trying to have as many parameters just into the 2D sketches. Let's try and do another one that will work. In this case, I could change, for example, the parameter for this conic. So this is a conic profile. It's not an arc from a circle. It's actually a conic profile. That parameter, I could change it to maybe 0.25 and wait. Okay, I'll go the other way. You can see the conic now is flattened. I'll go 0.75. Okay. You can see now the side's gone a bit more square, the side profile, and the model has actually rebuilt without any problem. So this could go directly to CFD, and we could test quite quickly this new profile. Okay. I'll click on the cross here, so it will cancel and come back to the original. It's done it. Okay. So this is what I call the master. The reason I call it the master parts, master body front, is because when you build composite parts, you normally start building a master, which is the general outer shape. Then you will build a mold, and inside the mold, you will build the final components that have got the correct thickness. So I like to create masters for the parts this way. Having said that, in this case, there is some thickening and thin parts built into the master. But I want to show you the chassis, which is a bit more complicated. But the master is more simple to understand. If I go into the chassis folder here, there is this tab called Master Chassis. Right. Here you recognize basically the general shape that incorporates the crash box, the nose of the car, the canopy or the roof of the car is there, and even the rear engine cover. So it's all coming from this shape. That's got 45 features, so it's quite nice. It's a big part of the car, but it's only 45 features. And it all starts off some sketches as well. The main one is this one, so let's have a look. So if I open my side sketch, that describes a lot of the shape of the car, just this simple 2D sketch. Effectively, here you recognize the height of the roof, which is defined at 980 millimeters from the floor. Okay. And the 2 points, the 725 is the minimum distance I need to have between my front and rear roll hoop for safety. So that's built into this model. And if I go to final here, that 50 degrees is the onset of the windscreen. I could basically change that and go to 40 degrees, for example. And you see that you've got now a windscreen that's a little bit shallower at the start. You see that that profile has changed. I come back one step, and the model has rebuilt without any problem. Come back one step here. You could imagine doing some big changes there. That's the radius connecting back to the engine cover. Let's see, let's imagine the engine cover is going higher. We need more space for what's under the bonnet here. I typically go here and I'd say, okay, I'm gonna add, I'll go to 350 here, and the whole back of the car is gonna increase in height. You can see that. Come back. Okay, so that's worked well. Now what will happen is if I basically accept this change, that master model will be updated to what you're seeing on screen. And then it will be distributed to the other tabs, the ones that are creating the panels, the chassis, and the whole document will be updated. There's a whole suite of parts that are using this master. The nose of the car, the chassis, the engine cover. So you can imagine the amount of computing that needs to be done to rebuild a fair amount of panels for the car, all coming from this master. In fact, I could show you. We are going to try just for fun. So if I duplicate this, I'm creating a new tab, and we're going to go and open the panel for the rear panel, the rear engine cover, I call it. So let's go into body. Okay. Here you recognize the panel that sits on top of the engine, well, the battery in this case. Okay. You see the profile there is coming from this profile here in the master part. If I click let's go on this, I would expect this part to rebuild. Now it might take a little while because it's done it. I said it might take a little while. It's actually gone quite quick in this case. Now you can see that the top of the panel has moved up, okay, because the master has changed. Having said that, we've got a small issue at the back. I look at this and I'm thinking most of the panel looks good, but we have this face here that hasn't been resolved properly. If I come back, so I would have to go back into the cover itself. In fact, this is the assembly. Let's go into the part studio where this part has been created. This is the part studio where I create the panels for the rear of the car. And we're going to isolate the cover here. Let's isolate this. Okay. So here you recognize that face that didn't rebuild properly. If I click on that face in the history tree, so I've got 61 features here. And you can see that, okay, I've got a split here. So it's highlighted the features that have been used to create that face. So I've got a split, and basically that's it. So, but if I clicked on the shell itself, so one of the surface inside, I've got a shell, and the shell is what's created the panel with a certain thickness. So if I double click on this, the panel is 4 millimeter thick. What I've done is I started from a master or something that's very heavy and thick, and I've clicked on all the faces I wanted to delete. And now you can see that that face hadn't been selected properly because the new shape for the engine cover has created this new face. Remember before, the top part of the cover was low enough that this face was not existing. So I would come back here, select this face, click OK. And now the engine cover would be finished properly. And it's got the new shape. And the whole document has been updated and everything's translated. So if I go to my CFD model, I'd go here, I'd go to my CFD model. So I'd do that before I go to Bramble, just to check that all the parts are working together with the new shape, okay? It's taking a bit longer to open everything. I'll take some questions in a second, actually. Just want to show you this. Okay. So interestingly, in this case, it hasn't been updated just yet. Let's find out why. Let's go to this assembly here, body. So it can take a little while. So to basically, so for everything to move. Actually, I've seen it move just before I left. Okay. So we effectively see here that we've got the correct shape. You see the engine cover that used to stop before the split now is gone further into the tail. If I come back to the previous assembly, okay. You see now the shape goes between the pillar before it was stopping early. If I, just to finish before the first question, I can now come back to my version history. That stores every single user inputs. Everything I do is stored here. If I look at the main, which is what I'm working in right now, the versions are snapshots that you cannot change. Once you've created a version, it's something that's it's like a marker in time. But all the changes that I've done today, I can look. I've done this today. Oh, sorry, April the 29th. So that was not today. I can basically go and find the first change I did today, which was a rollback of the bar. And all these changes is what I've done today. I could go back to, so the automatic update, it's something that these are inputs done automatically by the system when the software is updated. That happened 2 days ago. I could right-click here and say, I want to restore this state of my document to the main again. So what will happen is it will take the state that was valid 2 days ago and put it back as the main state. So I do that. And you can see here the engine cover has updated back to what it was. What's happened is it says that my last input was to ask to restore the state that was valid 5 days ago. So I know that whatever I've done today with you guys showing you around doesn't really matter if I did any mistake or deleted anything. I just come back to a state that I know was correct, and then I continue working. And now I've got the engine cover. If I come back to my previous tab, oh, I don't know if you've seen, but basically it's moved down, back down. So the whole document is updated back to where I wanted it to be. Okay, let me take some questions. Rain, please. And if you have any question, you can also type in the chat. Okay,
Hey
so you
Nico.
put your question in. Oh, hi.
Hey, yeah, so my question was, in this design process right now, are you already thinking about like the manufacturability of it? And when do you start worrying about like how you're gonna mount it, like the designing like the rivet hole, bolt hole locations and other fixtures?
Okay. Yeah, thank you. So that's a good question. And I will show you more design now to answer this question. The design as it is now is what I call concept design, but it's a very advanced concept design. So it answers the aerodynamic questions because that model is good enough for a very accurate CFD model. So it answers all the questions we may have about aerodynamics. It answers some questions about assembly, but not all of them. So if I show you again the panels, I would go to the easiest for me is to go back to the CFD assembly just to show you that. I didn't have to, but I wanted to have a first idea of where we're going to split the panels. So, and this is for a reason, in terms of practicality, and I wanted to understand what sort of accessibility we would have when we remove the top panel, which we know is an easy panel to remove. That because that will guide where we have some of the connections for the battery, for example, to recharge. So you can see that we know exactly the some parts like the crash box. You can see it's fairly detailed. In fact, in the crash box here, I put some location for the mounting itself. You can see it's not finished. We would need more details because the hole doesn't go through, but I wanted to have that so we know where the mounting will be, because that impacts into where the suspension damper and everything is. It's a packaging exercise where everything's going to be. So some questions are answered, but it's not finished. It will still require to completely to manufacture the car, have all the drawings ready for manufacturing. We still need between 5 and 10 designers to work for 6 months and detail everything with mounting holes and mating, assemblies, faces, and gaps and everything. But I wanted to answer as many questions as I could. Why? Because it also impacts some of the aerodynamic decisions. And you see, for example, the door, it's a sliding door. I think I explained that before, but it's not mounted on hinges. I want something very light for the 424 Nürburgring lap. So it's a door that you slide and it comes out of pins, and the door just comes out like a hatch. But obviously I wanted to have that detail in this model because that creates this sort of the sort of step on the chassis, and that can impact the aerodynamics. Okay. So it was important to, it's better than a conceptual model where I would just have put a surface and not think so much about the assembly. It goes further and have some realistic way of assembling the car. So I know where some, steps might happen, or the thicknesses as well. Having the door with the correct thickness, including that frame, you can see the frame here is important because it impacts into the size of the outlet for the air exiting the cockpits. So it has a performance impact. So everything that could impact the performance of the car is built in at the concept level for 424. We go a bit further. Obviously, this model has got a fairly simple shape for the caliper. This is the brake caliper. The reason is we are not allowed to share the full model for the Brembo brakes. So I've created more simple models that are used for the CFD model, and that's okay. And also is the public model for everyone to see. But if we go into some more intricate designs, if you go into the suspension, for example, and this is not the best one to show actually in this case. I want to show you the powertrain, for example. We've got two models for the powertrain. I'll explain why. There's one called rear end bevels, and a new one called the rear end. I'm going to open both and I'll show you the differences. This is a new development that happened 6 months ago, and the one that we're going to build is this one. So if I show you the differences, right. But I'm opening this so I can answer your question as well. So just give me a second. So here you can see the location of the motors is different. If I show you the powertrain itself, you can see here we had two electric motors connected to basically a mini gearbox made of bevel gears, 90 degrees gears, with a lay shaft, and then another box with bevel gear to the final drive. Well, this one is made. This is what we're going to build for 424. You see, the motors are closer to the diff, and we just have one gearbox with spur gears, straight gears. You can see the difference clearly. The reason I had designed this at the beginning was because I thought the center of gravity, we wanted more mass to the front. Being a four-wheel drive, I was worried that we were going to be too heavy at the back, especially because the battery is at the back. So I moved the motors away from the rear axle using this gearbox. But then when we did more dynamics, driving simulation, we realized, no, we want more mass at we want the weight distribution at 47, not 48.5. And actually, I'm happy with that. So that's why I've pushed the motors back nearer to the rear axle. But that allows us to build a gearbox with straight gears, which is actually more efficient. But you can see that these models, even though it's not a finished gearbox, they're actually really precise in terms of the dimension of the gears. And if you look closely, you can see you've got a gear, you've got space for the bearings. So obviously these models are conceptual, but I can tell you the dimensions are very, very close to the final dimensions. There will be, for the gearbox, I expect things to move maximum by 5 or 10 millimeters. And the reason is the packaging is quite tight, and the location of the motors is important to know, because then we have space for the suspension in front. Everything is quite close together. So I needed to understand that from a packaging point of view. The gearbox itself is going to be provided by a supplier. They're going to design and build the gearbox to these dimensions for us. So the shafts will be exactly in that location. The diameter will be really close, but they will make adjustments to adapt to whatever they can build and optimize efficiency. So that shows you the level of details we have. It's correct in terms of gear size for the ratio we want, but you don't have details of the teeth and things like that. But also the diff is correct in terms of packaging. I know we can have the differential I want into this volume. Okay. When it comes to the suspension model, the model you see here is actually a new model in terms of, this is the correct location for the wishbones and the push rods, but it's not detailed more than that. I've created this new model because I wanted to change some of the location for the push rod and wishbones. There is actually a better model in terms of detail that exists. You can see it here. So we had a designer called Isla, and he did some work a couple of years ago, and we actually went into more details. You can see we wanted to understand how the suspension flexures. You see here we're having blades that will deform, like on a Formula One car. So the wishbones are moving not around a spherical, but we have basically a flexure, and we have this steel part that will deform. It's lighter, and it's just a lighter way to do it. And in this case, the model is fairly accurate. We wanted to understand how we are going to mount it on the box with these two bolts. And in fact, that model is also detailed in terms of the upright itself. So if I show you this, we did a lot of work on how to mount the suspension members. I'm going to come back and show you the wishbone as well. In fact, I could isolate this. Okay. You see how this model is actually quite accurate. It's got the bolts, and the exercise here was lightweighting. I said to Isla, look, the features needs to be this, that. I looked at the kinematics, and then he went around different iterations of how to design the upright, given the bearings that we have and the axle that we had designed for the LMP1 some years ago, and just trying to make the assembly lighter and lighter. And we actually went a long way, and we gained something like 2 kilograms on the assembly over a period of 6 months of working together on this. Now, as I said, when we have the funding in place to build 424, we're going to have to basically take this model. There will be a new designer coming in, and he will redesign everything from scratch again. But we will have a lot of information to speed up that design, the final design stage. Basically, this will be the baseline, but I will ask that person to use the new kinematics of the suspension, which is described by this model here. So the wishbones have moved a little bit on this model. This is the more up-to-date kinematic model, but using some of the principles of the detail that we see in this model. Okay? And remember that on this type of cars or any high-end design process, you want the designer to be involved from finishing the parts to also following on the manufacturing. So quite often the designer is going to be responsible for communication with the manufacturer, making sure the drawings and the tolerancing is correct. So that's why we haven't invested further than these models into creating 2D drawings, for example, because I didn't know if that person would be the same person staying on the project until the point where we're going to manufacture. And it will be rebuilding a new team of people again to redesign the car and finishing all the parts and take them to manufacturing. But as you can see, we've got so many models and answered so many questions that when it comes to the point of rebuilding the last team of designers, I said 5 to 10 people who will take everything to manufacturing, this process is going to be really quick, actually, because we have already a lot of design to start from. So I hope that answers the question of what is the state of the design for the car right now. Any other question, please? Yes, Wesley. Hi.
Hi. You showed us the master model just now, which is the one that contains all the aerodynamic surfaces. Is it possible to replace one master model with a second one if you want to study the packaging for different aero surfaces? You want all your child to reference to a different model. Is it possible to do it in Onshape?
So I don't know if it's possible, to be honest. So the way the way the design works is it's obviously it's like a software with lines of codes, and you start with the sketches, you put some extrudes or rotate, revolutes, and and fillets, and then you split everything, and then you shell, and then you've got your panels. To actually replace effectively part of the tree, a section of the tree, removing it and replacing with a new section that comes from somewhere else. I don't think it's possible. Like it's you can't do it as easily as that. What you would have to do is remap everything. So when I say map things, if I go to the tab, okay, let's take an example. So I go back to my rear cover, I go into body, I go into the rear panels, panel front, panel rear. Is it this one? Yeah. Okay. You see the input for this part studio is a bunch of derived. What a derive is a link to another geometry coming from another tab, or it can come from another document. If I double click on this, effectively that links to the master chassis. It's the one we were looking at before. You could basically say, no, I don't want to use this. I want to use something. Even you could actually go and select something from another document. Could be your document or anything you want, or something else from this document. I could find another master here. You know, the master for the rear body. Okay, this is a bad example, but you can see, you can say, no, I'm changing what master I'm using. I'm going to click on this one, say, okay. What you're going to see is everything will become red, I think, because there is no association between the different faces that it needs to recognize so that the downstream product works. So you see now you've got basically you've got all these geometries that you see are the geometries we use to cut and split the parts. Obviously they've been created, but after that everything's going to turn into red. You see all the errors everywhere. Split 7 did not regenerate properly, so it will have one missing selection. Effectively, if you go back inside this, you see how it couldn't find the part to split. It's become red here. Why? Because I changed the master to something else that he cannot recognize. So in theory, you could go back and rebuild everything. It would take a while because there's so many features to rebuild, but it's possible. So you could do it this way. But you can see how the downstream steps all need to be looked at properly.
Understood. Very clear. Thank you.
Okay, no problem. So I've come back one step and repaired. Okay, any other question here? Yes. Project. Hi.
Hi, Nico. Do you use any named parameters and any mathematical relations between them and manage this formula somehow?
Yes, I do. Not very often, so I need to remember where I had some. Let's go and have a look at the rear wing, actually. I wonder if I've got some here. This is where the profile of the rear wing is designed. Let's have a look. I know there are some formulas somewhere. I'm trying to remember where. Oh yeah, of course. Okay. I will go and show you where the suspension is. In the suspension tabs where all the kinematics. Okay, before I go there, I just wanted to show you the rear wing model. I quite like this model. So this is where the main plane flap and end plates are designed. And you can see there's a bunch of you can organize your features into these sort of groups. I've got like an old F1 sort of sketch there that I created for the F1 car. So for 424, I reused a profile that I had for the F1 that I created in the past. And now the actual rear wing as a reference. The actual rear wing for 424 is described into this sketch. I quite like it because it only has a bunch of parameters. And I can tell you honestly, I've learned how to describe the rear wing or a wing profile for a F1 car or or LMP1 this way, and it works really well. And it's actually sections of basically some arcs that link with some conics. So here you've got an arc. I could change the parameter and you see the whole rear wing being rebuilt. So I can go to final here. Let's make it a bit clearer. And say I just want to, okay. Sorry about that. You see what we call the slot gap, that gap between the main plane and the flap, that distance here. So first of all, that 40 millimeter is more or less the thickness of the main plane. If I change that to, I'm gonna take the final off. It's a bit quicker. If I change that to 30, oh, you see how the main plane's got thinner, but everything else is still associated correctly. I still have this 3 millimeter fillets that matters for manufacturing and quality, and the gaps is maintained. You see how when I do a wing geometry, there is always a 2 millimeter straight edge at the end. That's for manufacturing as well. You cannot just finish by just a point. If I'd go here and say I want 4, and now that's thicker on the threading edge here. Okay, the gap I was talking about, I'm trying to find the dimension. By the way, you've got so the arc here, arc 400, I could go to 300. Oh, the whole wing has moved. Obviously, you've got, let me go back 2 steps. It's not very pretty, this one. Go back to my original. Here you've got the sort of description of the leading edge. That 90 mil is quite important. I could maybe increase that to 125. Now you've got a more progressive acceleration of the flow under the wing. And obviously, if I wanted to increase downforce, typically here, I would basically make the box bigger. So I would increase the expansion of the wing. So here is 170. I could go to 225. Boom. You see how the wing is much more pronounced. That would be a very high downforce one, maybe even separating. But what I want to show you here is the sketch has been built in such a way that you change one parameter and the whole profile still makes sense. You see how the flap has followed correctly. So I spend a lot of time building this. I really love just building these 2D sketches. And when they're working well, then you can just create a bunch of wings and test them in CFD very quickly. I'm going to come out of here. I want to show you the suspension because that will also show you the use of parameters. If you go into suspension here, and there's this one called kinematics. Now here I'm using a few pictures that OnShape has created, which is really cool. With the same set of, I only have 24 features here. And all I create is effectively 2D geometries. There's no 3D in there. You can see the number of parts is 0. But I end up having these sketches that describe where the push rod is. You see the low wishbone, the mounting points on the chassis, the top wishbone. That will be reused in the next tab, which is the suspension members. So the first tab is kinematics and then creation of the 3D parts in that suspension members using the sketches I just talked about. Let's come back to the kinematic. Okay, so what I've done here is I've used the ability to use configurations. What you see here is the front of 424, but if I switch to the rear, boom, you see all the sketches have been updated and now you're looking at the rear geometry. How did I do that? I go into the custom tables, or the configuration panel rather. And now you've got a table which is the front and the rear. And by the way, if I switch here, you can see it's switching as well. And each row is a set of parameters that describe all the kinematic of the suspension. So the first column is the axle location. So effectively, the front axle is on x0. So the front wheel is aligned with the 0 point on the x-axis for the car, and the rear axis is at x3000. So if I were to go on the rear, and if I just want to move the whole suspension, I just changed one number here. Instead of being at x3000, so the wheelbase for the car is 3 meters. If I say, okay, I want it at 2700 now, boom, everything's shifted by 300 mil. Come back. And then you've got other, so I come back to the front. And the way kinematic is built is using all this bunch of numbers. So one of them is the camber. It's difficult because you cannot put a name here, so you need to know which one you're looking at. But when I click on it, or it shows me in the sketches. So you've got the front kinematic sketch, this one, and then you've got the side kinematic sketch, this one. So the front sketch will have things like the camber angle of the wheel. So if I change that number, you will see straight away. If I go to an extreme number, say 10 degrees, boom, you see how the wheel has got 10 degrees camber now. This is the axis of the wheel, or this is the axis of rotation of the wheel. If I come back one step, back to 2 degrees. I could change my roll center height. So let's try and find it. So it's about, so the roll center height. If I'm not sure, I go back into the sketch and I know that it's described by, sorry, 120 here. This is the roll center height. This is the height between the ground. So we're at 40 mil ride height. The 0 is the floor, and the ground is 40 mil lower. And the distance 120 is between the ground and that line that goes between the contact patch and the intersection of the wishbone far away on the sides. So typically the wishbone angle is mainly defined by the roll center height. If I change that number, so it says I cannot change it from here, I have to go in the table. I wonder if it will see. So I still have to do it manually, find it. Okay, it's here. If I change my roll center height by, and I go to a low roll center, say 50, all the wishbones will flatten. Boom. You see how the wishbones now are horizontal. The reason we have a high roll center is because I need to attach the wishbone fairly high on the chassis. If I come back one step, well, the mounting point is constrained. What's changed is obviously the height of the wishbone into the wheels. So yeah, I have used lots of parameters in this case. With the same set of parameters, I described the front and the rear suspension. So let's do a little fun game here. If I go into the actual suspension assembly, so the final product, and I'm going to show you how I'm going to go back into one step into that part studio that creates these wishbones. And I will, let's say I only want to look at the front here. So let's say I want to isolate these parts. Okay, so we don't see too many things and it's a bit clearer. So I'm looking at the front suspension. If I go back into the kinematic table, so I'm really driving everything using this table here. Let's say I'm changing that camber to 10 degrees. The sketch is updated. Obviously, I don't need to be in the sketch. Okay, I'll do it again. Okay. Now, if you go here, that hasn't updated just yet. Why? Because we are using what we call contexts. You see the these arrows on the sides, it means that it's a way for Onshape to take some geometries that have been described, that are parts that have been described in an assembly. So you can build an assembly, position parts, and then go back into a part studio and do a context and use that as the new reference. You'll have to read more about this, but basically I need to go into the context and I need to update. So it's a manual step in this case. So if I update my context, it should put more camber. Just wait a minute. And obviously it hasn't done it for some reason. Which is interesting. Oh, I didn't do the right one. Sorry, I didn't do the camber. I did another one that was at 2 degrees. Okay, so we didn't see the change. This is the camber. I go to 10 degrees camber here. Now you see the change. If I go here, I go update, and surely, okay. Strangely enough, it hasn't updated as I wanted. I'll have to find out why. Sorry about that. I did it the other day and it worked. I'll try last time. Okay. I'll have to find out why. But, oh, it has done it here. Okay. You can see how the camber on the front wheel is very high now. You see, it's a bit ridiculous, actually. It looks weird. So that's how you drive suspension design through a set of parameters. Just to be sure, I'm going to go back here. Just like to be sure everything works. Let's say I want to update something that visually we can see. Let's say I want the wishbones to be more spaced out. So I would go into my front view. I can see I've got, I must have a distance. So this is the distance of mounting. Okay, the 190 here. So I need to find the 190 in the table. It's here. So I want the low wishbone to be lower, much lower. So I go to 125. I don't think I've put the correct 190. It can be a little bit tricky. That's this one to navigate. You see how the low wishbone is gone much lower. If I come back here, hasn't updated yet. I have to go here. And do a manual update of the context. I just like to experiment and make sure that all the links are working correctly. Okay. So it's taking a minute to load. Let me try and load it from here. I'll do it from here again. So sometimes Onshape can, it's not getting stuck, but sometimes some calculation take more time and the tab will not necessarily load as quickly as you want. Okay, interestingly now you see the camber is correct in this tab. Okay, so if I update the context, the wishbone should move. Okay. You see how the low wishbone is gone down. In fact, you can see the old position versus the new one. I can go to the assembly and everything's updated. Now you've got a low wishbone. You've got the camber on the front. Okay. So as I did before, I want to come back on all these steps. I'm going back here. Do you remember when I did the restore 5 days ago? I'm just going to basically go back here and say I want to restore that state. And everything will come back to normal. And you've seen it's done it already. Okay. So I hope that answers your question. Any other question you have, Rain?
Hey Nico, thanks for answering my last question. I had a quicker one. Um, the control arms for the suspension, do they have any, like, I know it's like the titanium rod ends and carbon fiber. Is there like any sort of core, or is the rod part of the control arms just carbon fiber?
It doesn't have any core, so it's going to be a tube that's hollow, basically. So I'm actually, let me open a document to show you that. Just give me a sec. I need to find it. So there is a document where the thickness of each arm is described. I like to show you that because it's quite a piece of analysis as well that's really important. Okay, so I've opened it here. I hope you can see it. Yeah. I'll explain in a second where that's coming from. Okay. So what you have here is for every suspension leg, track rod, push rods, and then wishbone lower forward, lower rearwards, upper forward, upper rearwards, for the front and for the rear. So every single leg, front and rear on the car. I have taken the analysis from Unity when we drove around the Nürburgring. From that, you know the maximum loads on the contact patch of the tire. And then I have another tool that basically calculates the load in each leg given a certain load at the contact patch. And then I've looked at the maximum and minimums around the lap for each leg. So you see, it takes time to do that. So what it tells you is that the push rod, for example, will see a maximum compression of 65 kilonewton. So it's a very high load. And no tension. It's always in compression. The rear is also 65. And as you can see, some legs are not very highly loaded. So if I look at the upper forwards is only 5 kilonewton in compression, but the tension is 50 kilonewtons. So you're picking up the min and max. It doesn't matter if you were compression traction. At the end of the day, the push rod needs to be dimensioned for a 65 kilonewton load. You can see there is a very high load on the rear wishbone. It's basically the rearward lower leg that sees a 70 kilonewton force on it. Then I apply a safety factor. I have a yield strength. This is using carbon fiber. And after that, I calculate a cross section that I need for each of my legs, given the loads. And based on all this, I end up having basically a thickness for the tube. So I calculate a thickness for every tube, and then I apply a minimum because the track rod, I don't want to build it at 0.6 millimeter thick. It's too thin anyway. So I always build at a minimum of 1.5. So it will increase even the safety factor. But obviously the push rod will be thicker at 2.8. So this is the thickness of the composites, but there's no core because it's just an empty tube. Okay. So having said that, the manufacturer might say we need a core just for manufacturing purposes, because when you build a tube, you need something inside so you can consolidate your composite in the mold. But it's not required for the final product. It's just required for manufacturing potentially. So every leg is going to be built at a certain thickness. You see the more highly loaded wishbone will be 3 millimeter thick, which is very thick carbon. Okay. So all I do then in the design at this stage, obviously I know the thickness I want to build each leg at, but actually in the concept models up to now, all I have is a profile. I come here, right? And if you look at the profile, it is an accurate profile for aerodynamics, by the way, but it is a profile. The model doesn't have the thickness at the moment. It will be for the designer to take the thickness I want, the outside profile that I've described for aerodynamics, and then build it into a component. Having said that, okay, these drive shafts are just tube, but I do have better drive shaft models that are a bit more accurate because I wanted to understand the mass of the drive shafts. So when it comes to the drive shafts, I can show you. If you go into this, the older model for the powertrain, okay. If you go into this tree, you're going to find some drive shaft models. This is quite a nice model here. You have a more accurate model here of the thicknesses. In fact, it shows you the thickness of the tube, which I've calculated from knowing the torque going through each wheel. And I wanted again to have a mass for the drive shafts. Okay, and they can weigh 2 or 3 or 4 kilos, so it's quite important to know them. And then there is a steel tube with the rollers here. But as you can see, it's still a concept model. It doesn't look like the final part that will be built, but it's quite close in dimensions. Okay.
Thank you, Nico.
Yeah, you're welcome. Yeah, great questions. Anybody else want to see anything specific? So for the last 20 minutes, I just want to show you. So we've covered quite a lot of CAD today. I'm really glad. I hope you see the level of, again, investment and time we spent into this. And again, actually, something interesting is some models have gone from being detailed to being concept again. The suspension, for example, we had a very detailed suspension with all the bolts and mounting for the LMP1. But with Isla 2 years ago, we've rebuilt a completely new model, which you see on screen now. Actually, the axle is still the LMP11, but the upright is new. And because I wanted a new kinematic model last year, I've rebuilt a completely new model that's not as detailed, but contains the better information for location and aerodynamics. So this is to explain that what matters to me is the ability to keep developing and finding performance and lightweighting, better mounting position. The day, again, we say, that's it now, we are going to build a car, we're going to have to redesign it to a new level of detail with a new team of people, as I said. But you need to build a model to the detail level you need just to answer the questions that you need. And that's what we've been doing for years now. But we have answers for, most things to do with performance. So I'm glad. So if I go back to this, to the discover.perrin.com website, and as a last section, I've put 3 design stories, and I'll let you spend more time if you're interested to navigate through them. I'll open one of them. But again, thank you, Alex, for creating these documents. As I was designing or doing the aerodynamics, or Isla was designing, Alex was just gathering all the images and creating these amazing documents. If you open the rear suspension one, for example, this has got more than 100 pages, I think. But you're going to be able to see how models have evolved. This was the suspension we had for the LMP1 back 10 years ago. That was done by a designer called Antoine, and it was it was our starting point, and we were ready to build this if we had sold the car at the time. But it's quite different to the models we have now. So we started from there and started rebuild, creating new models for the upright. This is for the rear suspension. Okay. Trying different ways of mounting the wishbones. This is it. You can see it's even different from the last model I did show you. So you could go through these documents and see the different tests we've done. You see how now the mass has been reduced to 2.5 kilos. Various options of how we've been creating some pockets for lightweighting here. And also we've done some stress analysis. At the time we were using a software called SimSolid. We even did stress analysis on the wheel itself for braking case. Stress analysis on the uprights. So we've gone a long way into doing various studies here. Decided to change the push rod position. Then we have a new version of the upright, a bit more simple. You see how the upright mass is now gone down to 2.1 kilos. It was 2.6. So, you know, a lot of lightweighting going on here. But you cannot do this if you are not able to do stress analysis at the same time and verify that it's still going to work in terms of stiffness and strength. That was another model. This was 1.9 kilos, but we've gone back a couple of steps on this. So again, stress analysis on this. We do multiple cases. This is the braking case, vertical load only, and the lateral force. Now we're creating these kinematic models that I was showing you to create new updates, you know, certain locations for the kinematics I wanted. There's a lot of work in terms of packaging with the wishbones. Typically at the rear, the wishbones are quite close together, but that creates fairly high load on the suspension legs. This is all to do with the aerodynamics. So there is a compromise between you know, the diffuser volume and the top body, but still allowing enough space for the suspension to be stiff enough. Looking at details of how we mount the push rod on the low wishbone. Okay, and again, more packaging analysis. This was still using steel push rods, wishbones and legs. We moved on to the carbon ones a bit later. Now we sort of looked at rotating the caliper around the uprights, again to try and find a better lightweight geometry for the upright itself. In fact, we've got a purely, this was actually a caliper being at the low part, since it has moved back on the side just because the cooling is a bit easier to achieve. Little bit of an animation here. So at this point, we wanted to have a motion analysis to get the exact position of the wishbone at different ride heights. That has been done all in Onshape. You can do motion analysis in the assemblies. And then we put the bodywork and see if we have any interference. In fact, here you can see there is a problem here. We go back to SimSolids and do some more analysis. If I move, so there's a lot of slides here. What you'll find is we also do this analysis where we put, you see the bars here we put on the wheel, and this way we can measure the stiffness, so the camber angle change and the toe angle change with the loading on the tire. So we've gone a long way in looking at these details. And in the end, I think is you're going to start seeing, so we've got more details on the upright and lightweighting pockets here. So Islas spent a lot of time to do a lot of good work that will be reused for the final version of 424. How to mount the push rod again with the bolts and having enough thickness left into the metal here. Okay, so if you're interested, have a look at these documents, and then finally the assembly of the drums and the cooling system around the brakes. So this is the rear suspension one, and just finally, if you're interested, you can open the aerodynamic one, and that will show you some of the changes that has happened between the LMP1 Le Mans and the Nürburgring version of the car. And it's a step-by-step document showing you some of the steps that were made to develop the aero package for the Nürburgring. In fact, I want to show you this. So this was the initial DRS concept. I thought that it would be interesting to move the lower gurney on the bodywork. You see, we had an actuator at the bottom and one at the top for the flap. With more CFD analysis, I realized that rotating that top gurney didn't do much for drag, but it would have been quite difficult to build as an assembly. But the top flap is what makes the biggest difference. And then we went to the pneumatic system, and I realized we need 2 actuators. So that's why now we've got 1 and 2 in the pillars. Okay, so I'll take a couple more questions. Okay, so Ray?
Yeah, hey again. I just wanted to know if you've put any planning into like the bearing selection for the uprights, like whether you use ball bearings or needle bearings, or like if you have any thoughts on that.
Yeah, absolutely. So we've worked with SKF on that. The work we did was at the time we did the LMP1 design, so 10 years ago, and that would need to be maybe updated, but we have a really good baseline, if you like. In fact, if you look in the documents, you will find some bearing analysis for the LMP1. So I want to see if that is built in this model, but maybe not. But let's have a quick look. Here you go. You can see the bearings here. So these are angular contact bearings. So you've got 1 and 2, and they're typically they're called high diameter, low profile. So they're very thin. They're small, but they're high diameter, and they're angular contact with a preload. And the preload is basically set using a spacer here, the yellow spacer, which I'm going to highlight. That spacer has got a certain width that is basically defined. So when you bolt on your axle using that screw here at the back, you bolt on it will basically apply the exact amount of preload you need for the pair of bearings that you have. So it's a typical assembly of wheel bearings for this for LMP1 and F1 cars. Okay.
Okay, thank you, Nico. Much appreciated.
No problem. Okay, I'll take maybe a final question or two if you have. But yeah, I'm really glad we've covered a lot. I hope you've learned, things about the details of how the 424 is designed. Hope you've learned a little bit about the On-Shape tool as well, and the philosophy of how I've designed this car, with obviously the help of Antoine and Isla and more designers that have been involved along the way. Okay, so let's leave it here. Okay, Wesley has got a question before we leave.
Yeah, you mentioned that you need about 5 to 10 designers for 6 months.
Yeah.
Have you considered how many areas are you going to split your car into, and what will be the role of these 5 to 10 designers?
Yes, sure. Yeah, thank you for the question. So if I think of the car, so you're gonna need one person to just do the suspension, the outboard suspension. So the wishbones upright, the work that Islan had done for the front and rear, one person for that for at least 6 months. It might take even a year. Then you're gonna have another person on the inboard suspension, which is where we've got the springs and dampers and also normally the person who does that will do the pedal assembly as well, the steering system. So anything that sits inside the chassis that's close to the suspension. Then so the transmission will be done by an external company, and they will do the detailed design themselves using the concept that we have. But then we have the composites design. So the chassis, the panels, the wings, and I think that you will need maybe 2 people to do that. Maybe 3 people just for the composites, because there's a lot of panels, assembly to be detailed, and there is also like structural analysis to do on that, insert designs. So quite a lot of work there. And it's not the end. After that, you've got obviously, so the battery system is going to be done by an expert company that will come ready, but the integration of the mounting of the motors and the mounting of the battery, that will also need to be looked after. We have things like well, I talked about there's so much composite on this car. So the rear casing, we used to have an engine and a gearbox and some metal, but now it's a lot of composites instead. So at the back of the car, where the motor fits and the inboard suspension, you've got a big rear casing composites. So that's another thing to do. And I'm trying to think, but there is obviously more areas after that. The windscreen, this is more or less composite design, because it's thin parts and holding and holes and bolts and things like that. So yeah, quite a lot of work. Just that team will need to work really closely with me and take ownership of certain areas. Oh, and the cooling system as well. So the radiators and the pump and the pipes. And then there's the electrical system, but the electrical system, the high voltage will come with the motor and the inverter and the battery. But there will be some design for the low voltage, but that comes more at a sort of drawing level for harnesses and things like that. So yeah, there is a lot to do.
Thank you.
Okay. Okay, everyone. So thank you for joining the session tonight, and I hope to see many of you in the next one next week.
Thank you, Nico.
Cheers.
Thanks.
Thanks for
Thank you,
joining.